So a few last persons are joining, and I think waited for a couple of minutes and can start with our workshop today. I first want to introduce our two speakers, our two presenters from overseas this time. It's Simon Horton and Florian Herla. Simon Horton is from Avalanche Canada, an avalanche forecaster. He recently completed a postdoctoral fellowship at the Snow and Avalanche Research Program at Simon Fraser University, so with Pascal Hegeli, and probably most of you know that this group is driving at the moment the machine for future development. So it's very cool, Simon, to have you here. Simon is a huge specialist and has a lot of experience. He graduated at the University of Calgary with Bruce Jamieson. And since his PhD, Simon has been exploring the use of SNOWPACK, so the snow cover model from SLF Davos for operational avalanche warning. He has developed a couple of products that are in use at Avalanche Canada and will allow us to take some insights, especially on how to visualize model data. He will give us an introduction in how forecasting is performed at Avalanche Canada, and then put more insights on the operational use of SNOWPACK. The workshop is built up as follows. So Simon will start with his presentation, which will last about 20-25 minutes. Then we have 20 minutes for a discussion. We'll make a short break. And in the second part, Florian is giving us some details on how research is supporting those wonderful tools from SARP. And again, this will take 20-25 minutes, and we will have plenty of time for discussion afterwards. Florian Herla is at the moment PhD student at Simon Fraser University in the Avalanche Research Program by Pascal Hegeli. He's actually from Germany, studied meteorology at the University of Innsbruck, and is certified mountain guide. He's primarily concerned with how SNOWPACK models can be matched, validated, and improved with SNOWPACK information recorded in the field. And all of us, we have to congratulate Florian. He is on honeymoon. So congratulations. And we start now with the first speaker. Simon, please, floor is yours. And I'm very excited to hear your insights. Thank you.
Yeah, thank you very much for the introduction, Christoph. Let me just share my screen here. There you go. Are you able to see my presentation now?
Works nicely. Perfect.
Okay, thank you. Yeah, and thanks a lot for inviting us to this conversation. I'm really excited to hear a bit about your thoughts on this, because really this whole idea of SNOWPACK modeling originated in Europe. And we've been experimenting with it here in Canada in the last few years, doing some things to bring it into our daily workflow, but it's very much a new idea, and we're really open to ideas and collaborations on different ways we can do this to support forecasting. I'll also mention that for Florian's presentation, we want to acknowledge Stephanie from the SLF, who's recently been working with Florian on some of the tools that they're using for SNOWPACK research. So I was going to start off with a really general overview of the forecasting program at Avalanche Canada. And that's because some of our unique context and data sources has really shaped the motivation of how we use SNOWPACK. So Avalanche Canada is the home of public avalanche safety in Western Canada, or all of Canada. Our main goal is to empower recreationists to travel safely in the backcountry. So unlike some other regions in Canada, there's other organizations of avalanche professionals who deal with infrastructure, transportation, guiding, and we're really just focused on backcountry recreationists who are going out on their own, trying to give them the information they need to plan a safe day in the backcountry. And we have a few different programs and services that do this. One is our daily forecasts. That's where I'm involved in. I'm producing the daily forecasts. The second is we have a standardized education program that we coordinate, and that's delivered to all backcountry recreationists in Canada. And then we have a variety of outreach programs, including social media, presentations throughout the winter, and youth programs that are all kind of targeted to raise awareness about avalanche safety. We're a nonprofit organization, so we rely heavily on funding from our government partners. And we work closely with other avalanche professionals and also get quite a bit of funding from the private sector with the number of partners and sponsors. I'm just showing there all the people who support us here as an acknowledgement. So going back to kind of our main user group, this backcountry recreation in Canada, and there's a few unique things about this context that I think are relevant here. One is there's quite a diverse number of activities in Western Canada. Motorized backcountry use is roughly similar number of people going out as there is backcountry skiing and snowboarding. And then in recent years, we've seen a large increase in the number of hikers and snowshoers heading into the mountains as well too. And so we have to kind of take into account the different ways these different user groups interact with avalanche terrain when we're setting up our education and forecasting programs. And for example, snowmobilers can travel much greater distances and move through terrain in different ways than a skier does. Our 10-year average is 10 fatalities per year, and they mostly occur in Western Canada. There is some avalanche areas along the East Coast where we do have some programs running, but most of our focus is in the big mountains of Western Canada. And a big unique thing in this area is that a lot of the recreation is in large remote wilderness areas. It's quite uncommon to get cell phone reception. And if anything goes wrong, people are typically pretty far from rescue. And this really plays into this idea of having people set up to be self-sufficient and make their own decisions in the backcountry. We kind of structure the forecast as a starting point to kind of form a basic trip plan, but we try to give people tips and through our education ways to validate that forecast when they go out. And that's also partly because our forecast regions are so big that there's variability within their region. Our forecasts have to be general summaries of the conditions in these big areas. So you've probably seen something like this before, comparing on the left, the map of Western Canada with the forecast regions in yellow. And this is pretty close to scale, I believe, with this map of the Alpine countries of Europe. And we could see that many of our forecast regions are similar sized to European countries. So we have a big range of areas we cover. Also quite a diverse set of climates from up north in the Yukon, which gets quite a bit of Arctic influence. The southern coast down near Vancouver and Whistler is very warm and maritime with very heavy snowfall. And then as we move inland, we get the full range of transitional and continental climates. So Avalanche Canada is responsible for 15 forecast regions in Western Canada. There's another 6 regions that are smaller and they're managed by the parks. Most of them are in the Rockies. These smaller regions are done through a slightly different workflow where the park staff are heading out into the field and writing the forecast often in the same day. Whereas for us, we're office-based forecasters who do all of our forecasting out of the Revelstoke office. So we spend the full day in the office relying on external information to build our forecasts. We do have a number of field teams. This has been growing a lot in recent years, who work for Avalanche Canada and go out and collect information to support the forecasts. And they send that information through two-way communication to the Revelstoke office. And then on a typical day, there'll be 4 forecasters working who are each responsible for 3 to 4 regions. We typically group them up into quadrants like shown on the map here. So one forecaster will have to be tracking the conditions in all of these areas. And these ranges can still be quite long. It's with regions several hundred kilometers apart and a lot of variability within them. So as I said, we're based in the office and our day typically starts at 6 a.m. with one forecaster coming in to do a review and possibly making some morning updates to the forecast. The rest of the forecasters start at 9 a.m. and spend the morning analyzing observations and looking at the weather forecast. Around noon, we meet with professional meteorologists at Environment Canada. So we're not trained professional meteorologists. We have more of our experience and skill from actual field work in the backcountry. So we rely quite heavily on this relationship where we can ask the professional meteorologists more detailed questions. Then through the afternoon, we'll start making our hazard assessments. A key part of our workflow is around 2 p.m. All the forecasters get together and have a discussion about the next day's conditions, talking about our uncertainties and also about how we want to communicate that to the public. Then finally, we write our forecasts for the next day that are published by 4 p.m. And also throughout the day, we'll do some other things like correspond with the field teams, potentially media interviews, and other forms of written communication like blogs. I'm definitely going to talk about data sources because that's really going to lead into where snowpack modeling is fit in. And traditionally, our biggest source of information is from other avalanche professionals. And we have this great system called the InfoX, where different professionals submit and share their observations each day. There's roughly, I think, now over 150 different subscribers to this service. It includes backcountry guiding operations, highways, industrial sites, and each day they submit both their field observations as well as their localized avalanche forecast. So we're able to see all of their local assessments of danger ratings and avalanche problems. And this is super valuable. Definitely in some regions where we get a lot of professional reports, we can really wait on their expertise to produce our public forecast. But we also have areas where there's not as much information coming from these other professionals. And to address this, a number of years ago, we developed a crowdsourcing platform called the Mountain Information Network. It's basically through an app where anyone could submit photos and observations. And we've really encouraged this. And this map below here kind of shows the number of reports we've received this season. Typically a few hundred per forecast region, and forecasters read all of these reports every day, and they've really become an important part of how we collect our information. We have adequate coverage of weather stations. Most weather stations we look at are run by other government agencies, and we are directly involved with about 5 or so weather stations in more remote areas. But our coverage is still pretty variable. There's some big forecast regions where we only have maybe 2 or 3 weather stations that are giving meaningful information in terms of high elevation weather. So we definitely kind of did some data issues in terms of weather station coverage. And then finally, weather forecasts, which, as I mentioned, we work closely with Environment Canada, who give us a number of products and briefings on the weather in our regions. And one specific thing I want to mention about our weather forecasting is that, again, with these large regions, we often have to look at the variability of weather within that region, because quite often a weather system could impact one part of the region, but not the other, resulting in quite different avalanche conditions. In the past few years, we've done quite a bit of work on building tools that help visualize this data. And this has really been done in parallel with some of our work on SNOWPACK modeling, and a PhD student with Pascal's program, Stan, who's works in data visualization. And he's been really working on tools from that help highlight big scale patterns in the data, as well as identifying and helping forecasters understand uncertainty. And this kind of process of understanding the forecaster needs and process has really been a big driving force in how we're designing our tools. So these are just two screenshots of interactive dashboards. The one on the left shows individual avalanche reports on a map and various ways of mapping out the different types and locations of these avalanches. On the right, it's a weather station viewer where we can look at basic summaries of the main weather patterns that are driving avalanche conditions. So taking this context and our data sources into account, there's been a few motivating factors that I say have really kind of driven the way we've tried to use SNOWPACK in Western Canada. The biggest is this data sparse issue, where a lot of regions we don't have a ton of data, especially field data. It's fairly common in some of these areas to mostly base our forecasts on weather information from the weather stations we have and the weather forecasts. And as you can probably imagine, you could do a decent job of forecasting new snow and wind drifted snow types avalanches. But when it comes to forecasting persistent weak layers and old snow type problems, it gets a little challenging to do that just off weather. So that's one place we've been looking into how SNOWPACK can help. Similarly, early season conditions can also be data sparse, especially since a lot of our professional reporters don't really start until late December. And at that point, there can often be 2 meters of snow in the mountains with several notable weak layers that are causing problems. The second motivation is this idea that we have these large regions with variability within the regions, and having some tools to help understand that variability would certainly help improve our forecasts. And the third motivation is just some of the traits of our SNOWPACK that we often deal with really tricky persistent weak layers like large surface hoar, facets on crests, and the types of avalanche problems that are notoriously tricky to forecast. And so it would be great if we could use some SNOWPACK modeling to get some help and basically a second opinion on what kind of weak layers are in the SNOWPACK and how they're behaving. Cool. That was my kind of summary of how our program works and where SNOWPACK is fitting in. So I was going to jump over now to how we've actually used it so far, some of the impressions that we've had from forecasters, and that will lead nicely into Florian's talk, where he's working on addressing some of the current limitations.
Simon, maybe you give us a tiny little bit of a chance if we already have some questions for you.
Yeah, this, absolutely. I can...
very, very summarizing and very interesting introduction into the whole topic.
Mm-hmm.
Do we have anybody? You can use your the raise hand function or just drop your comments in the chat and we try to moderate them. Like I have a question that I observed on one of the slides. If you can go back like 3 or 4 slides. It's a surprising question. It's exactly on this slide. One further. Yeah. If you go one further. Where's the difference between surprises and naturals? No, you're 2 further, I think. Yes. Here, this one. Avalanche observations. I very much like this dashboard, and I kind of got hooked on surprises versus naturals versus controlled versus explosives.
Oh. I didn't realize you'd be able to read that like small fuzzy fonts.
Yeah.
I was trying to avoid that detailed question. Yeah, so typically our avalanche observations reported through the InfoX have come in a tabular format where we look through and read these tables. And the experienced forecasters got pretty good at reading the raw text tables. And basically Stan kind of did some interviews and observed how forecasters were reading these tables to figure out the types of things they were looking for in them, and kind of building the design to highlight those things. So one kind of thing that forecasters were often really trying to look for was any kind of skier accidental or remote triggered avalanches. I believe we kind of pulled a couple of like these specific trigger types, and here they're called surprises, but basically it's any kind of avalanche that would maybe catch the attention of a professional like that.
Okay, because it looks like, I mean, this is very much way too detailed for this kind of discussion, but it's interesting how you like kind of got the surprises out of the naturals and the controlled ones are kind of connected to the explosives. But yeah, this was a kind of off-topic question, but just to start the day of questions, this is a workshop. All of you are invited to ask questions. And here we have Matthias in the, what do you want?
Yeah, Simon, you told us that, you showed us how big the forecasting regions are in Canada. And you said that there are many forecasters actually working every day on producing these avalanche forecasts. How is that like organizationally managed? How many forecasters are working per region, or are there like, how is that organized?
Yeah, I think we have approximately 20 forecasters on staff, and a typical day there'll be 4 forecasters working. And one other forecaster who's kind of overseeing some things. So each forecaster will be responsible for about 4 regions, typically, right? 4 forecasts in a day. I did have a image that, yeah, here these blue circles are showing kind of the groups of forecasts that would be covered by a single forecaster. Okay, so there are several forecasters forecasting the same regions. They're communicating with each other, coming to a consensus, and then is that how it works? I assume that there is not only one forecaster for 3 regions. Oh, no, there is. It's only a single individual who will write 4 forecasts. There's no one else duplicating that. So when they have their discussion, the person forecasting these northern regions will listen to the forecaster who's forecasting the south and help them think about these conditions, but they're not spending much time looking at these other regions. Oh, okay. So there's one single forecaster who is looking specifically at the conditions there, but there's not a second one he is like talking to and adjusting with, or? Correct. It's largely one individual. And they'll only bring in other people if they have specific questions or like want a second opinion on something, but it's not okay. Always. And then you mentioned the field teams which are out there. So what information is provided by the field teams? How often are they communicating with the forecasters in Revelstoke? And also, is the forecaster in Revelstoke specifically telling the field team what information he needs? Yeah, it's a pretty collaborative process. So typically the field teams work 4 or 5 days a week on a regular schedule. And most mornings or the night before, they'll correspond with the forecaster and discuss what the main uncertainties are. And so together they get some input on, or ideas on what kind of information or what area to go to would be most interesting for that day. So often the field teams are quite aware of their local conditions and have really good ideas of like these are our main uncertainties. We want to go here and look for this type of condition. But they also do listen to the forecasters' questions as well. Thank you.
Thank you, Matthias. And I think with this, we go into the next part and you take us from the forecasting, how it used to be or how the surroundings are, into what SNOWPACK offers you into the whole process.
Yeah, absolutely. Thank you. So our approach to using SNOWPACK has been to really use it to get a regional scale summary of the snowpack patterns. Even though like the model itself was kind of designed to like be next to a weather station and give you a really detailed scientific analysis of all the layers in the snowpack, we've been trying to like modify that to go very general and regional scale. with the main idea of helping us identify avalanche problems. So we can see what regions or what parts of regions would have a new snow problem versus an old snow problem. And since we're working in this really data sparse environment, we've done this by forcing SNOWPACK with outputs from an NWP model. We use a single weather model from the Environment Canada at a 2.5 kilometer resolution. And this started over 10 years ago with Bruce Jameson and Sacha Belair. And I don't know if Sacha's on here now, but he's returned to the Alps after this. And I've kind of been picking up and continuing what he started. And it's really been iterative where kind of each winter we've developed a few prototype tools for the forecasters to test. Then we've collected their feedback and worked on the designs. And 2 years ago, we got to the point where this became a more stable operational product that forecasters could use more regularly. And certainly there's been a lot of increase since then with forecasters looking at these tools and starting to think about ways that they could help with their forecasts. And this iterative process has also been really helpful to identify the main challenges that are prompting our current research. So to get this regional scale coverage across our forecast regions, we pull weather forecasts from about 1,200 different grid points. We don't run it at every location across our regions because that would be tens of thousands of snow profiles. But we do this process that selectively samples a few representative grid points that cover different areas and different elevations to kind of capture some of these main regional scale patterns. Then at each of these locations, we produce a virtual snow profile with the SNOWPACK model. And we configure the model to really be flat, sheltered terrain. We don't look at the effect of slope impact or, for example, solar radiation on south slopes. We also do not look at wind transport. We kind of turn off those switches in SNOWPACK. So the idea is that all these profiles would be what you would possibly find in a flat sheltered area. And we think that's most helpful for identifying new snow and persistent slab type problems. But certainly with this setup, it's not really equipped to help us with wind slab type avalanches. So our current product has 4 different ways we visualize this data. I'm just going to ask, is this animation playing for you guys? JT?
Yes, it is, Simon.
Okay, thanks. So our first visualization is fairly simple. We have about 100 key locations, and at each one of these locations, we can view the profile at that point. And we do that with a layout that's pretty similar to how NIVIS would visualize any other output from a SNOWPACK model. We have a timeline of the SNOWPACK history on the left, and then a hardness profile on the right. And this is just a kind of our interactive dashboard that lets us browse these quick and efficiently. Then we want to go kind of looking at more patterns with all 12,000 profiles. We can go to maps, and we have some map layers where we can view some of the key parameters like new snow depths, total snow, and we're definitely tweaking this always for whatever kind of data we can pull out from the SNOWPACK models and throw on a map. And here's a screenshot of 2 of the more interesting ones. The left, this is a map of new snow height with this scale that kind of turns to yellow once you get over 25 centimeters. So in this case, we can kind of see along this coast, these areas where there's deeper accumulations of new snow and probably a decent likelihood that we're dealing with a new snow type problem here. And this is all just based off the model's calculation of settled snow height. This is going to be quite a nice complement to our weather stations, which are often quite sparse and trickier to see these regional scale patterns from just a few point weather stations. On the right here, it's a little more experimental, but we're trying to pull out an basic index that gives the likelihood of some kind of persistent weak layer in the snowpack, where the darker shades of reds show profiles that have more persistent weak layers. This is just definitely more of an experimentation of how to show that. I think there's a lot more that could go into this kind of calculation of a persistent weak layer map, but in kind of really two simple glances, these two maps can tell you roughly where you might have a new snow problem and where you might have a persistent slab problem. Our third visualization is what we call a regional summary. And in this view, we simply click a forecast region and you get a graphic that shows all of the profiles in that region. This image here kind of shows our basic layout that we use, where we split the profiles into 3 elevation bands with alpine on the top, tree line, then below tree line. On the left, we show a single representative profile, which is calculated as the average of all of the profiles in the region. And on the right is a graphic that shows all the individual profiles at that elevation band. So the idea here is on the left, you can see the most common type of snow profile. And on the right, you can see the variability within the region. And I think Florian might touch on some of the details of how we actually do this, because that was a fair bit of work to figure out how to make this average a meaningful calculation. And then finally, our most recent type of visualization is what we were calling clusters. And there we do more detailed statistical comparisons of all of our snow profiles and sort them into groups. So on this map right here, we have the different colors show the groups of profiles that have a similar structure. So for example, each of these colors are represented by these profiles shown on the sides. And on the background of the map, we can see our permanent forecast region boundaries. But then with the coloring, we can see some of the main differences within that forecast region in terms of a snowpack structure. So those are our 4 current ways we view the snowpack, and they've all been integrated into our forecaster data dashboard, which means it's accessed the same place where those avalanche observations and weather stations are viewed by forecasters. So with that, they're able to access it daily. And I would say it probably varies between individual forecaster and the avalanche situation on that day as to whether they use this tool, but they are easily accessed daily. This winter, we've also introduced a weekly snowpack briefing, which is typically I'll lead. And we spent 15 minutes just discussing the basic patterns in the snowpack models, a discussion on whether or not they are accurate, because these are all unverified predictions. And then sometimes going to other like specific training exercises, because these are still kind of new types of information for all of us, and we're very much learning how we can use it. We've also shared this visualization dashboard with a number of other forecasters who operate in the same areas. And I don't have as good of a handle on how much they use it, but my impression is that they don't use it to the same extent that we do at Avalanche Canada. So a big part of this process has been collecting feedback from forecasters. And certainly through these weekly discussions, I've learned a lot about what other forecasters get out of these models. We've also done a number of different surveys, interviews, and observing forecasters doing their work to get some ideas of how they use it. And I would say to date, most often these models are used for looking at new snow depths. Like that map I showed is people find a really quick way to figure out where there's currently snow. And for a general sense of what areas have weak layers and how deep those weak layers are. But kind of take these to the next level, I think a lot of forecasters are interested in going in more in detail into the properties of the weak layers, the properties of the storm snow, kind of get into some of the more details that will help really forecast the size and likelihood of avalanches. As well, this year, we finally kind of had a bit more discussion about looking at snowpack temperatures to quantify warming and wet avalanches, which is something I know has been tested a bit more in Europe. And then overall, I would say in this past 2 years since having this operational tool, there's been a big increase in the number of forecasters who look at it and understand it. They're not looking at it as a kind of true prediction of this is what the snowpack's like, but rather using it as a starting point to kind of prompt some questions to be like, oh geez, I guess there's like, looks like the models are showing some kind of crust layer 50 centimeters deep. So I should like go back and look at reports and past weather to see whether this is an actual problem. And then, not surprisingly, the biggest limitation is knowing whether or not these models are accurate. Verification has been a big challenge, especially in data sparse areas where there really isn't good information to verify the models. And this has been a head scratcher of a problem that we've known about for years and haven't had a clear way to approach it. And Florian's going to talk a bit about some promising methods we have to help us assess how accurate they are. So in the past 5 years, our research and development is really focused on modifying these snowpack models to do this regional scale coverage and visualize it in a way that forecasters can quickly look at and pick up on the main patterns. But now we're at the point where we see our next priorities as building in ways to better verify or assess the accuracy of these models, and do more work on summarizing the information to pull out details that are relevant to our avalanche forecast. And I think that will tie nicely into Florian's part of this discussion. So I'd summarize by saying we've slowly been implementing snowpack models at Avalanche Canada. And a big part of that has been a user-focused design where we really have listened to the needs of the avalanche forecasters and tried to build tools that help them with their largest problems. And this iterative process has been, I'd say, a good success so far, especially with getting us to the point where we have relatively simple and easy to understand visualizations. And there's hope that we can further develop this to support forecasting in these large data sparse regions that we deal with. And with that, I'll thank you and I'll stop sharing.
Thank you, Simon. Thank you for sharing. I think this has been quite impressive. And maybe now we have some questions for the first part of Simon, who now introduced us to all the, very advanced actually application of SNOWPACK and a lot of new visualization tools, which is like my first question would actually be just putting these two things into perspective. Is there any new understanding actually, or are we simply working with the same tools just in a very different way and in a very different visualization? For sure, it's an enhanced tool. But like from the basic understanding, I think, did something really change?
Not really. The main concept is taking the weather data from a weather forecast model and putting it into just the normal version of SNOWPACK. And I'd say from our end, one of the biggest things that's changed is the quality of our weather forecast. The high resolution NWP modeling has gotten so much better in the past 5 years even that we're able to just kind of use these unverified models more frequently.
So in the end, you do something like you did not jump from the horse on the car, but you probably went from the horse wagon and used the wheel and put it on a car. Still the same wheel, but it's on a different thing. That's at least how I see it. There's a question from Leo from Corinthia, who is asking about a technical question, which is how did you do the dashboards? Is it Shiny? I guess Shiny is some kind of programming language for dashboards.
It's all done in JavaScript, and the specific platform is what the developers at Avalanche Canada use for all their tools, and it's called Svelte, is some kind of JavaScript framework that they're building this in.
And there's way more questions concerning the dashboards, how available. I know that there's this one paper where you actually published the dashboards. So is it possible that you share some links or you comment on how can you use the dashboards in which way, and which parts of it are, like, I would say, closed or proprietary for Avalanche Canada, and which parts are available to the public of people to play around?
Yeah, a few comments there. We published a paper a few years ago sketching out general ideas of how we could visualize SNOWPACK information in more interactive dashboards.
What was the title of the paper, and whoever's first puts the link in the chat?
Enhancing SNOWPACK models with visualization design principles. And visualization design was this kind of framework that we were introduced to, that's all about understanding user needs and presenting data not in a scientific way, but in a more abstract way that people think about their problem they're solving. And then I'll say that at SFU, Florian and I have been publishing a lot of our code, the underlying code, on Bitbucket. Our profile analysis is done in R, and we've been publishing a few packages to CRAN. So a lot of the underlying code is kind of openly available. In terms of the actual dashboards, at this point, it's just internal at Avalanche Canada, but it's really not too complex. Most of the complex stuff happens in preparing the data.
So maybe you or Florian can also share the Bitbucket link, because there's apparently a couple of people which are pretty much into programming and would like to know about it. And I already see that Carsten was so nice to share the link for the paper for everybody in the chat. Very cool. I would say you use the wheel. It has been on a horse car, and now the wheel is on almost what is a Canadian Ferrari?
I don't think that's coming through in English.
No, it doesn't really, but I can at least try. Let's go back to the clustering, because you showed the clustering. I think Florian is going to talk more about the clustering. Mm-hmm. And can you go back on the slides, because I think this was a little bit fast for everybody. Oh. And in the clustering, yes, exactly right here. So similar structure. Can you comment on how structure and avalanche problems are related, or what kind of, we've lately heard a lot about the the SLF, I would call it the SLF way of talking about different kind of typical profiles in a soft slab, hard slab, and so on and so on. So what kind of structures are you talking about, or is this the part of Florian, and are they connected to any avalanche problems?
Yeah, this is definitely something that Florian led the development on. And it's really, we kind of made up a new way of calculating similarity, not based on the full detail in the profile, but more so picking up on key features. And we kind of played with subjectively some different weights on what kind of things would group profiles that forecaster would say, these profiles all look like they have one type of avalanche problem and these have another. So the things that are weighted heavily would be the amount of new snow and the presence of weak layers or crests and their approximate position in the snowpack. Like, is there a weak layer in the bottom of the snowpack, in the middle, or near the top? So, and I believe he's also published that similarity measure in his first paper. But the idea here is, yeah, it's not a full numeric saying these profiles have rounds of these densities at these positions. It's more of a subjective way of grouping them based on avalanche problems.
Okay, cool. Thank you. Like, then we have two questions with raising hands here. One is from the Avalanche service right here in Tirol, I think. You guys, the LVD crew, do you want to pick up and turn on your mic?
Yeah, thank you. Yeah, we were wondering about the numerical weather prediction model you're using for the SNOWPACK simulation. So I guess for the future, from the day you're looking at the SNOWPACK models, you're probably using the operational models from your weather service. But then for the past, because you're already also showing the whole seasonal development of the SNOWPACK, so are you, is that some kind of a reanalysis or analysis data set you're provided by the weather service as well?
No, it's not. It's actually using past unverified forecasts to do the history. And I guess at the early stage, we looked at the reanalysis products we had from our weather services. And just since there's relatively few observations in the mountains, it was often lower quality, the analysis, than the original model data, just because the few weather stations we have are in valley bottoms, and the analysis tended to smooth out and reduce the amount of precip in the mountains. That being said, we are involved in a project right now with our weather service to give them some more of our high elevation weather observations and improve the analysis. So I think if we could better assimilate the weather observations we have in the high elevations, that would certainly be a more logical thing to put into these simulations.
Okay, thanks a lot.
Thank you. And then we have another one from Froni. Froni, you want to post your question?
Yes, thanks. I was wondering about slide 28, if you could go back to slide 28. Yes, so you said you were using the NWP weather prediction models to run your simulations for reference points, I would say. And now it looks like you have regions covered according to these simulations. So these regions of yellow and bluish colors, are those reference regions that refer to these reference points, or how do you connect the simulation, a point simulation, to these regions? Or is it a misunderstanding?
No, you cut off that really well. It's a good detail. Yeah, so for one, drawing these as region polygons makes for nicer visualizations than dots on a map.
Yes.
And the way that we currently do this is we looked at our weather forecast, or the NWP model grid, and we formed groups of areas that had similar forecasts, kind of these little small homogeneous subregions, and then just pick one weather model point out of this somewhat homogeneous group. So the idea here is the zones on this map typically all have similar data coming out of the weather model. Okay,
so they are like somewhat climatologically connected, the places in these
exactly, yes.
regions, and the regions themselves, they are constant. They don't change according to the weather. They are just constant regions, and you have 1 point per region.
Exactly.
Okay, and I have actually another question for the where you showed you have the 3 reference simulations for above the tree line, below the tree line, and the alpine. Yes, and how do you actually read the right part of this graph? So
so this is a design that's described in more detail in that paper that Karsten shared, but essentially this top one, it would be the easiest to read. And it says there's 3 profiles. So there's each of these bars is representing 1 snow profile. The colors represent the grain type. So here yellow is new snow, the purple is rounds, and green is a crust on the bottom. And it's sorted from depth with 0 on the surface down to ground.
Okay, so
for here, there's 3 profiles that range in depth from 200 to 300 centimeters.
Okay,
and the depth of new snow ranges from 30 to 60 centimeters.
Okay, thanks. That explains.
Sticking to this, and then we go to another, then we kind of have to blend over to Florian, but maybe sticking just here and the colors. So facets are in the role of surface ore and depth ore is like your deep or dark purple stuff, which is potentially weak layers, I guess. But why is the other, and now you said like the purple is usually the rounded grains. Why does it not make sense to like, or are all the weak layers then the dark purple ones? Or how could we identify them in the best way?
Yeah, the idea here is that any actual weak layer that would be an avalanche failure layer is colored dark purple. This color scheme, it's also from that visualization paper, was just one way to try to simplify the main patterns in a single glance to kind of use fewer grain types, again, kind of pointing to avalanche problems. So the idea here is you would look at the yellow to identify a new snow problem, and then look for the structure of a light purple slab over a dark purple weak layer for a persistent problem type.
And potentially even on a crust. Thank you. Then there's 2 short questions. One was from Lindsay, but I think it's pretty much answered, which is to the spatial resolution of the NWP model.
Yep, 2.5 kilometer.
That's a simple answer right here. And then Igor from Italy, he's asking us what the computational load for these simulations is. This like real time on the fly, or like when do you get the weather data and when do you have the plots kind of?
Yeah, so we run it at 4 in the morning, and it typically takes about just over an hour to run it for all of our locations. So that way they're prepared for the forecaster who starts at 6. The 2 most intensive processes are, one, we have to convert our weather model data from GRIB to NetCDF, and we have a net, that way it can easily be read by SNOWPACK. We kind of prepare it into a format that's automatically read by SNOWPACK. The second biggest computation load is some of the snow profile comparison calculations that Florian showed. And there's ideas of how to optimize that, but right now it increases exponentially the more profiles you try to compare in a group, because it does pairwise comparisons. So those some of the statistical comparisons of profiles can take up to half an hour to run.
Okay, cool to know. There's one more question. If the LVD crew doesn't have a question anymore, maybe you put your hand down. If not, keep it up, then you're up next. And there's one more question from Matthias, and then we have to go towards the next talk.
I know that just fits in quite well here. You mentioned that you had to choose representative grid points because you cannot run the model for every grid point. How did you choose them, and how many are these?
So yeah, that's been something I've experimented with kind of every summer. And I would definitely say I haven't found the best way to do this so far. Right now we have about 1,200 grid points. And that was largely just through analyzing. There was one season a few years ago where we ran SNOWPACK at every single location. So I have that one data set to look at how homogeneous local profiles are, and could get a sense that we only really needed one for every 10 kilometer square grid approximately.
Okay, so that doesn't mean you chose representative profiles, but you just realized that you don't need that many in order to represent the region. That's why you choose less to make it more efficient. Okay, thanks.
Thank you. Thanks for the questions. And LVD crew, do you have another one?
Yes. the forecasting regions are quite big. Do you intend, with the knowledge of the clusters from the SNOWPACK regions, to split the forecasting regions into micro regions to give out different avalanche problems?
Yeah, that's definitely something we're looking at right now in ways that we can better resolve these big forecast regions. And SNOWPACK modeling could help inform this in some way, but we need to have a better sense of how accurate it is, especially if we go to finer resolutions. Right now, for some of our very large regions, we can feel somewhat confident when it's saying there's a new snow problem on this half and an old snow problem on this other half of the region. But we're definitely looking at a lot of other factors like our available data sources from the field as to how small we could split up our regions.
Okay, thanks.
Thank you. Thank you, Simon. Thanks for the discussion and the questions. And I think we go over to Florian because time is passing. And Florian, you're up next. Do we already have your screen?
Thanks, JT. That's great. Thanks for the invite, by the way. All right, so let me share my screen here.
Yes, screen is up. So if you have more questions, as we said before, use the chat or use the raise hand in the discussion afterwards. And there's Simon is also going to stick around and you can ask questions to Simon. And now Florian is up.
Perfect. Thanks, JT. Hi, everyone, also from my end. And yeah, thanks, JT. Thanks, Matthias. Thanks, Christoph and Axel for having us here. From Simon's presentation, you got a good understanding as to why SNOWPACK simulations can be useful in Canada's forecasting. And you also got familiar with some of the challenges that we face in that context. I want to reconnect to these challenges and highlight once more that the data volume that we generate is just simply too vast and too overwhelming for forecasters to go through manually in their daily routines. And that's why we need some numerical tools that help us make this data more accessible in meaningful and relevant ways. And then on the research end of things, a challenge that accompanies the need for these numerical tools is that we're dealing with a quite complex data format, which is the snow profile. I guess you're familiar with the challenges alongside it. Snow profiles record the sequence of many layers, and each of these layers can be described by many different properties. And then usually between different profiles, layers shift in their depth, they are missing entirely. So in short, we just see a large degree of variability between profiles. And so numerically extracting detailed information from large snow profile data sets has been challenging in the past. And so my objective for this presentation is to introduce you to some of the research we have been doing that aims at making large-scale SNOWPACK simulations more accessible and useful for practical applications in avalanche forecasting. And as Simon mentioned already, our current priorities are developing tools to aggregate the large amount of information and then to validate the usefulness of our simulations. And I'll split up these topics into research on summarizing profile data first. This project is basically finished. Simon just gave you a first preview on the operational application of these tools last winter. And then I'll demonstrate how we plan on validating our simulation, which is an ongoing project. We'll make a break after that. And actually, we might not get to the optional part 4 on clustering because we have quite a good discussion going. And I think that's more worthwhile than spending more time presenting. That's not going to run away. We can capture that in a seminar next winter. So a while ago, we implemented a tool set of algorithms whose root objective is to compare pairs of snow profiles. And here you see 2 hardness profiles where the colors refer to different grain types. I'm basically using Simon's color scheme, but in a little more detailed variation. So you can distinguish between round grains, facets, or rounding facets here, for example, new snow in yellow, crusts and melt forms in green. And then salient red and salient blue refer to predominant weak layers, so surface wear or depth wear layers. A crucial step in comparing these profiles is to understand which layers correspond to each other. So we need a layer matching algorithm. And our layer matching algorithm is based on dynamic time warping, which is a well-established algorithm that was developed in the 70s for speech recognition. So essentially, we take a similar approach as your everyday digital voice assistant that talks to you through your smartphone. And instead of warping time, like in time series of voice recordings, we warp snow depths, so that layers that originally are located at different depths or have slightly different layer properties can be matched. And by now we can do that not only for pairs of profiles, but we can apply that algorithm to entire data sets of profiles, which actually sped up the process quite a bit. Simon mentioned earlier that we need to do pairwise comparisons, which take quite long. With this new method, we brought the computation time down by about an order of magnitude. So computations that took 30 minutes before take roughly 3 minutes now. We pick one profile from the data set and we match all layers against it. And then we can create a new profile that inheres the prevalent layers and layer properties from the entire data set. And that new profile is sort of an average profile that contains the predominant layers from that set. And for many of you, that should be a fairly familiar concept because it is inspired by what we call a representative whiteboard profile that is usually drawn by forecasters and guides to maintain a mental model of the snowpack conditions in a specific region. So both of these human and numerical summary profiles aim to identify the predominant layers within a region that we're usually concerned about. So essentially, we can create snowpack summaries that allow us to synthesize the large volume of data into an overall perspective. And here you see about 100 profiles from individual grid points from within a forecast region, which are all valid at the same day. And to clarify that once more, so you see the grain type sequences of the profiles only. So each of these columns would refer to one snow profile, but not showing the hardness, only showing the grain type sequences. And in total, there are about 100 profiles next to each other here on this slide. We can compute a summary profile for that region at that day, and we can do so for every day of the season. And so the idea is that the summary profile gets you a first overview. If you're after when certain layers got buried, when storms hit, how much new snow they brought on average, you can consult the time series of the summary profile. And if you still want to dig deeper, you can pull up the individual profiles from the individual grid points and investigate the difference, for example, between shallower and deeper locations. But in fact, the summary profile is also much more than only this visual product. It's actually like a spider web that silently connects all the layers for us. And that in turn means it enables us to track layers across space, identify where they exist, where they don't exist, or it enables us to compute ranges of layer characteristics and their spatial distribution. So here, for example, you see for each layer, the percentage of grid points that have more than 5 lemons. Lemons are called Nieten in German. So in other words, we're looking at the percentage of grid points that structurally promote fracturing along each of these individual layers. And here, for example, the surface hoar, also die Oberflächenreifschicht close to the surface stands out. So let's just assume now we're interested in the depth distribution of that layer. Here we go. We see that it's indeed buried, very shallow, maximum of 10 to 15 centimeters of snow on top. So you're probably not worried about this layer right now. But if there's a storm rolling in, then you want to have this on your radar probably. So you can basically name what you want to know, the grain size distribution. Most surface or crystals are around 10 millimeters large. What about the elevation distribution of all profiles that have a weak layer in mid-snowpack? I don't want to draw your attention to any specific detail here, but I want to illustrate that we envision the summary profile to be a starting point to provide overview, but it can also facilitate retrieving all sorts of details on your demand. And the good news is that this data exploration tool is as good as the simulated data that it makes accessible. So when the model simulations get better in the future, the data quality that you get out of the summary profile increases too. Let me give you an example. Stephanie Meyer at the SLF recently developed a brand new and very exciting stability module for SNOWPACK simulations. And instead of consulting the simulated lemons, or again, Nieten here, we can consult Stephanie's new stability tool. So here you see, or here I overplotted the time series of the summary profile with Stephanie's new stability tool. So the more black color you see over the original layers, the more of the underlying individual grid points suggest instability in that layer and at that day. So for example, you can see that a weak layer formed at the snow surface in the first half of December, subsequently got buried by a big storm, and that led to pronounced instabilities at this weak interface. These instabilities lasted for about 10 days before they tapered off. I think now is the time at the latest, probably, or hopefully, when most of you must be jumping up from your chairs and asking one question. Does it work? Do these simulations actually add value? And how accurate and trustworthy are they? I need to manage your expectations right away. Can't give you a full and comprehensive answer to that question, but I'm currently in the midst of performing a large-scale validation study that looks at the last 10 years at 3 main forecast regions in Canada, one in the Coast Mountains, one in the Columbia Mountains, and one in the interior of the Rocky Mountains. And in the following, I can give you a brief insight into one season at Glacier National Park in the Columbians to demonstrate how we plan to validate the capabilities of our simulations in capturing these persistent weak layers and old snow problems. So let's build up some of the data that I compared during this study. Here you see the avalanche danger rating at tree line elevation for the entire winter season of 2019. And I pulled this data from the Avalanche Bulletin database, where I also have access to the reported avalanche problem types or the likelihood of triggering avalanches each day, and so on. I'm particularly interested in specific weak layers that are tracked by avalanche forecasters. So in Canada, forecasters maintain a database of tracked weak layers to facilitate communication among each other and to monitor layers that may wake up after new loading. So in this database, you find persistent weak layers that the forecasters were concerned about at that time. And most likely, these layers also produced a number of avalanches. It's worth it to note that this database is purely internal and is not available in the public Avalanche Bulletin. So in this panel here, you see the times when a specific tracked weak layer was associated with an avalanche problem by a forecaster at a given day. Let's add the time series of the summary profile for better context. And let's have a closer look at the example of the December 9 surface hoar layer. As the name suggests, this is a surface hoar, also Oberflächenreifschicht, that formed before December 9 and got buried by a storm at December 9. And we can see that this layer is captured by the summary profile with strong red and blue grain type colors. And we can see from the black dots in the upper panel that this layer was deemed to be problematic for roughly 3 weeks. The layer is captured by the summary profile, but let's also have a look at how many individual grid points contain that layer. That's visualized in that middle panel, which shows the proportion of grid points that contain that layer from 0 to 100%. So in this example, all individual grid points captured the December 9 surface hoar layer. We can repeat that exercise for all tracked weak layers of that season, and we see first that all of these layers show up in the summary profile, and we see that between 40 to 100% of the individual grid points contain these respective layers that the humans were concerned about at the time. And that's already pretty encouraging, but something is still missing, I think. Imagine you go dig a pit, a snow pit in the field, and you have identified all layers and structural properties. What's next? What do you do? Well, you likely perform a stability test, right? So let's try to do the equivalent with our simulations and overlay the new stability tool from Stephanie that we just got to know earlier. So again, the more black color you see over the original layers, the more individual grid points suggest poor stabilities in that layer and at that day. And with the information we see here, we could already make pretty good comparisons between the human assessments and the simulations. But let me pull up the relevant information more strongly for you. I added gray and black bars. These bars represent the proportion of grid points that are characterized by poor stability at a given day. If the bars are gray, any layer of each individual profile has a poor stability. And if the bars are black, exactly the same layer that the humans identified as being problematic is also characterized by poor stability in the simulations. So I do understand that this figure must be quite overwhelming at first. So let's again pick the example of the December 9 surface ore layer. In the beginning of the time period that I enclosed by this black box, the danger rating was low. Not a single grid point suggested any instabilities. We see that because the bars are at 0 at that day. So perfect agreement. In the lowest panel, we see that new snow falls in the subsequent days, which triggers the surface ore layer and other facets that just got buried. As a response, the danger rating increases to danger rating 4, high hazard, and simultaneously all grid points suggest poor stabilities. That's why all the bars are all the way up at 1. And not only that, but they actually suggest poor stabilities in exactly the December 9 surface ore layer. That's why the bars are black. So for the next week, the danger rating remains considerable and even increases to high for 1 more day. And all the grid points echo that assessment with poor stabilities in almost all grid points. After this prolonged time with elevated hazard, the danger rating drops to moderate and then to low. And we see the exact same trend in the black bars decreasing to 0. The next storm rolls in, and yet again, both the danger rating and the bars go into a parallel trend of elevated hazard and suggest instabilities. Of course, a word of warning here. This demonstration is 1 weak layer case in 1 season, and it only covers a specific situation where model world and reality line up quite perfectly. Not all simulations that we see look like that, but I want to emphasize that we're comparing 2 extremely challenging data sets with each other here. On the one hand, a data set of human assessments that can contain inconsistencies, subjective biases, particularly at times of sparse data. And on the other hand, a highly uncertain model simulation by a weather and SNOWPACK model chain. So the fact that we do see generally good agreement between these 2 data sets, of course, with exceptions to the better and the worse, is extremely encouraging. On a higher level, here are the different scenarios that jump out to me during my validation. First, there are times of stunning agreement between human assessments and simulated data, periods like the period we just looked at. The 2 key factors that seem to contribute to this excellent agreement seem to be that the weak layers that were reported in the assessments are well captured by the simulations and got loaded by new snow at almost identical times as we see it in reality. Then we see times of generally good agreement. That means that there are a few discrepancies between the human assessments and the simulations, which causes uncertainties. And it's not always obvious which information source to trust more. And that heavily depends on a variety of factors, I guess. And I think it's almost easier to make this judgment call in real time as opposed to a few years later in a research study that only has limited access to each situation. These uncertainties are often related to the question of which layers exactly cause the main instability at a given time, or how much new snow actually fell, which then firmly influences the degree of instability of buried weak layers. I guess that is a challenge that is that you're very familiar with in your forecasting chair. And we see times of rather poor agreement. And interestingly, that's very often the case in the early season. So Simon already explained to us earlier that in the early season, when professional operations have not yet started their business, forecasters can find themselves forecasting based off of weather information, but very few snowpack observations. While surface problems like the new snow problems or wind slab problems may be forecast fairly well, I would almost suggest that the snowpack simulations are more trustworthy to diagnose buried weak layers, especially during this period. The other case that sometimes leads to poor agreement is a missed or a delayed snowfall event that the models did not accurately capture. And this error then throws off the stability predictions as well. In reality, this is a challenge with weather models that we all know very well. And I think in real-time operations, you have your way of dealing with that kind of uncertainty. Last but not least, I want to mention that it appears to be a rare case that all our grid points miss a pronounced weak layer that will be of concern for long. So in other words, our model chain indeed seems to pick up the main regional patterns of the snowpack. And hence the take-home message from this validation exercise should be that snowpack simulations can indeed add value to avalanche hazard assessments as an additional independent information source. And this take-home message is informed by our validation efforts on the one hand, but it also echoes the feedback that we have been getting from forecasters over the past year, as Simon mentioned earlier. Okay, so let me wrap things up. The overarching objective of the research that I presented is to make snowpack simulations more useful for operational avalanche forecasting. And to make the volume of data that we create accessible in meaningful ways, we developed algorithms that enable us to numerically process snow profiles. The main task of these algorithms I showed you are comparing and summarizing of these profiles, as well as extracting all sorts of underlying details and distributions from these big data sets. We are currently using these tools to analyze our spatially distributed simulations. But in fact, these tools are equally powerful to analyze ensemble snowpack simulations. Ensemble techniques are a crucial component of modern weather forecasting, but applying these techniques to snowpack simulations was not overly meaningful so far because it was simply too challenging to extract all the relevant information in an accessible way. And something that is very new to us as well is that we started to include stability considerations into our simulations. And that was certainly motivated by Stephanie Meyer's work at the SLF, which resulted in this very exciting and new stability tool. This is actually a great example for a brand new improvement of snowpack simulations in general. Also, weather models, products will become more and more accurate. And simultaneously with the tools that we design, we aim to help bridge the gap to operational applications. Another of our priorities is validating our simulations, both with respect to new snow amounts and with respect to weak layer diagnosis. And our goal here is to build tools that help forecasters use the simulations and learn under which circumstances they work and when they don't. We believe that validation needs to happen on a large scale, potentially continuous format, similarly as in modern weather forecasting. At the end of the day, the forecasters working with these products need to get familiar with them and learn how to interpret them. And that's where we are trying to get to. I'd like to acknowledge the supporters of our research. And with that, I'll pass it back to JT and Axel.
Thank you. So it's either me or Christoph. I don't know if Christoph is already back. If not, you have to talk to me. But there's already the first question of Matthias, so I pass over to Matthias.
Thanks, JT. Thank you, Flo. This was just an excellent presentation. I do have a question, like a very general one with regard to the aspect. Why are you not producing models for different aspects and just for flat terrain?
Yeah, that's a good question. In the beginning, we were very excited to do the same thing. And we're actually in my validation study, I'm not only validating flat field simulations, but I'm also validating virtual slope simulations. So virtual slope simulations in the four cardinal aspects, north, south, east, and west on a 38-degree slope. But what we see is that there might still be challenges in this simulation, and we might not get a lot of added information out of this added computational load. So far, from our first insights, it looks like we're best off with flat field simulations only, where we extract the main general patterns of the regional snowpack and not go into too much detail, which is introducing new uncertainties that the models are just struggling with at the moment.
Mm-hmm. I was just wondering, because you're certainly missing aspect-dependent weak layers that way.
Yeah, absolutely. Yeah, I'm considering the weak layers and the avalanche problems on their different elevation and aspect bands and sectors. So yeah, I'm running the validation with two different configurations, basically the virtual slope simulations and the avalanche problems cropped to these individual sectors, and then the flat field simulations and the avalanche problems. And yeah, so far we see only more complexities introduced by this, by this enhanced detail, but not necessarily more value out of it. So that's the main driving force at the moment. Yeah.
And maybe Flo, you can again share your presentation and go back to that comparison with the profiles of the Glacier National Park.
Mm-hmm. Maybe I interrupt for 1 second because we have a nicely related question in the chat. And you can go back to the presentation. Oh, this is hard, going back to the presentation and listening at the same time. But because you are talking about the different aspects, and Andrea Meyer has a question kind of related to this, slightly related to it, because she's talking about wet snow instability. So again, a little bit to also what happened with Simon. Are you strictly, for example, sticking to avalanche problems and relate the profiles to avalanche problems, or can you directly identify wet snow instability? Or I would then probably relate it to the avalanche problem of temperature or warming in that sense.
So my concern is primarily with the individual layers. So we're on a long journey, I think, here. And I think the goal will be to extract avalanche problem characterizations from these simulations. But right now, my focus is primarily to individual layers. So these individual layers can, of course, be surface hoar layers, or they can be crusts, or they can be melt forms.
Or like in the sense of Andrea's question, then it would be melt forms. So you could easily detect like layers that recently developed with melt forms. So melting is going on, which then kind of goes into towards the wet snow instability.
Yeah, exactly. That would be possible within the capabilities of the model simulations. And I need to say that we're not dealing so much with wet snow problems in avalanche and in Canada. So we're not too experienced in SNOWPACK's capabilities in modeling wet snow cases, but I think Christoph Mitterer is just the expert on this question. So
yeah, he would probably give you the wet snow, the index, LWC index.
Yeah.
But back to Matthias, who was having one more question.
Yeah, I was wondering, maybe Steffi, I saw Steffi is here as well. Maybe she can answer that question as well. But how is poor stability defined in her tool?
Yeah, I was expecting that question, Matthias. And yeah, it's good to hear that Steffi is here. Hi, Steffi. Yeah, I don't think I'm in the right position to talk in much detail about her stability tool. It's brand new. And I think it would be very worthwhile for you guys to invite her to a proper seminar And I know for a fact that she has many interesting and exciting facts to share about this tool. And everything I can say is that we have been using it for this preliminary validation, and we see it working really well.
Mm-hmm. And from your conclusions, did I get the message correctly that if we could actually match actual profiles, kind of adjust the SNOWPACK models with real data, that we could increase the performance of these models quite a bit to detect instabilities?
So this question kind of addresses updating model simulations when they kind of deviated from the state that we observe in reality. So data assimilation and model correction. We certainly are thinking about this, and this is certainly one of the projects that is lined up in our sequence of future projects. But yeah, I think first of all, we need to get an understanding of how our models perform without any correction, and then we can try to think about how we can feed meaningful information that we collect in the field into these simulations. In the beginning, we thought that actual snow pit observations might be an opportunity, or at least filtered through an expert filter. So these whiteboard profiles could be one way to assimilate information into the SNOWPACK simulations. But at the time, I'm more working with these databases because I think that they actually contain more trustworthy data, because that's what the forecasters work with and have to work with every day. And the whiteboard profiles is really just, well, a sketch on their whiteboard behind their backs, basically. So yeah, these are my thoughts to assimilation right now, but yeah, definitely a future item. Yeah.
Mm-hmm. Thank you.
Before I pass the word back to Christoph, I also have one more question about the synthesis process, because like you showed it very nicely on the one slide, and your question, or you told us, or the question on your slide was, how does it work? So how does it actually work? How much magic is in there, and how much basic maths are in there? Or is it like, does it also involve a lot of geospatial analysis in the sense of where the profiles are and how you weight them? Because it doesn't look like a normal operation, like you add 5 profiles and divide by 5. So where's the crux? Where's the magic?
Yeah. So maybe let me go to this slide here to kind of illustrate the answer on that. So it's basically only mathematics. It's optimization. So what we do is we check how similar each of the different layers are to each other in the 2 profiles. So if you see that one blue depth hoar layer up here, that will be compared to every layer in the other profile. And then there are constraints. So it doesn't make any sense to compare this layer to the snow surface up here, or to the bottom. So there are constraints within that, but basically we're trying to see which layers has the best match. And then it's not only about the best match of one individual layer, but the whole picture needs to be correct. So the sequence of matches needs to be as good as possible. So it's an optimization problem between a number of layers of 2 profiles. And then, as Simon mentioned, in the beginning, we could do only these pairwise comparisons. So it would take ages to compute representative profiles and to actually analyze the data. But with that new method that we implemented, which is also not an invention that we did, it's a tool from the data sciences that we adapted to the world of SNOWPACK modeling, is that we do not compare pairwise profiles, but we match all layers from a group of profiles to this one representative profile. And that is now an iterative process. And yeah, in the end, we end up with this average profile that kind of summarizes and aggregates the information that is contained in that data set. So there's no magic in it. It's optimization, yeah.
Thank you. And I hand over to Christoph.
Thank you, Jan Thomas, and thanks for leading the discussion. Are there any other questions out there? Now is the time to ask them. You see that we have 2 of the finest specialist on this topic worldwide. So use the opportunity and ask questions. Otherwise, I do, and I promise I have plenty. So no questions at the meantime. Simon, before you talked about verification, do you have a very difficult topic? So what's the truth? Is it the snow profile you observe, or is it the one you model? Do you have some strategy on that, or some thoughts how you plan to perform your analysis on verification?
Mm-hmm. We have one, what I feel is like a relatively simple approach that we're pretty close to ready to implement. And that's simply comparing total snow depth. We have a decent number of observations from that between the weather stations and our professional observers, kind of across all of our regions, maybe 200 observations per day of snow depth. And I've worked on some visualizations that compare that observed snow depth with the modeled at corresponding elevations. And it's a really coarse tool, but I could generally say if the modeled total snow depth and the observed agree, we can have more confidence in our simulations. But then there's certainly some areas or situations where the model depth is half of what local observers are saying. And so there I would have less confidence in what the model's predicting. It's a nice simple one-dimensional. It's a simple one-dimensional variable compared to the multi-layered complex stuff Florian's looking at.
Keep it simple at the beginning. It's always good. And regarding to that, do you have already some routines where you do any calibration over the season? Because your SNOWPACK simulations are purely driven by the NWP, right?
Mm-hmm.
Maybe satellite stuff or something like that on SNOWHYPE.
Mm-hmm. We don't assimilate any of that into the simulations. We do, though, have some visualizations where you can compare the modeled and observed depth and kind of get on a quick map where there's relative agreement and disagreement. And right now I'm considering whether there's enough information there to apply a bias correction for the next year's simulations based on the past 2 years. This region has over or undercalled precip by 50%, because there's pretty good evidence that the biggest source of uncertainty in these predictions is the precipitation input. So I think that's kind of the quickest type of fix we could apply.
Yeah, true. Thanks. There's one from Leah. Very hypothetically, what do you think would be the biggest challenge if you wanted to expand the operational application to other large data sparse regions, for example, Alaska? Availability of weather data, snow ground truth, or institutional hurdles? Come on, there are no institutional hurdles. Simon.
Yeah. The first one comes to mind is just having the technical setup of coupling a weather forecast model with SNOWPACK, because every weather model kind of has some of its own unique data formats and characteristics. And I know it took me pretty much a full summer to link up the Canadian models with SNOWPACK in a way that could be done in big batches.
Okay. So linking the data between the NWP and the SNOWPACK model.
It probably depends on the different meteorological services that provide the models. I imagine some would be easy, and maybe some work has already been done to link ones that are global in domain. And I think we'll likely start seeing more higher resolution global models. So then it would be much simpler to kind of have a more standardized setup that could be applied anywhere.
Yeah, I know that Nander Weber put some effort into linking GFS with SNOWPACK, so it should be out there.
Mm-hmm.
But that's of course very coarse.
Mm-hmm. Yeah. And I guess it is worth noting the institutional ones. Yeah, there's definitely a challenge in training and getting people to understand what these tools can and can't do, and really treat them with like a critical or inquisitive kind of mindset, not just treating it as a profile, but using it as a starting point or a thinking tool to prompt more investigation.
Yeah. Okay. Then Leo from the Avalanche Warning Service in Carinthia is asking, how do you deal with triggered slabs in the validation, or do you use them for validation?
Yeah, to this point, we haven't done any verification with actual avalanche observations.
So future things to do?
Yeah, I know in other contexts, some of the newer avalanche detection networks give a pretty good data set of natural releases. And I think there's pretty good potential to do some calibration in these areas that have the automatic detection, because you get a pretty good coverage of where and when avalanches occurred. Human triggering, I think, is much more complex because it's kind of this likelihood of triggering if you were to apply a load.
Yeah, true. You probably are building up one of the most extensive natural avalanche recordings along Highway 1 with all those systems. So probably have enough data to validate in a couple of years from now.
Exactly.
I was very surprised that you showed in your presentation that your forecasters are quite confident with the weak layer location and that stuff. So you use SNOWPACK for that, I guess, a lot.
In a very coarse scale.
Regional.
Regional. A good example was this past winter. We had a big atmospheric river forming a widespread crust layer. And we knew that it existed up into the lower Alpine for all of the southern interior regions, like around Revelstoke and south. And we had also in those areas a lot of professional observations from ski guides. So we kind of knew that existed there. What we didn't know is as we moved further north into our Caribou and Northern Rockies, where we don't have many professional observers, whether that same structure existed. And we weren't getting reports of avalanches, but we also knew that there weren't people out there to report. So then we looked at the model profiles and compared and saw that in the areas where we knew this crust layer existed, it was shown in the profiles. But as we moved further north, that crust layer disappeared from the profiles. And it was kind of a supporting piece of evidence that, okay, there's some reason, there's maybe more reasons why we're not seeing avalanches up there. It's not just that there's not observers, there's also likely not this structure. It was probably a different weather pattern during that event that formed the layer. So that's just an example of a very regional scale tool.
Yeah, but it's very cool and promising that your forecasters are getting confident in those layering stuff, and the forecasters in Europe primarily get very confident in the wet snow stuff. So by the matter of fact, I know that many centers are purely basing their assessment on wet snow avalanche cycles on SNOWPACK now. So it's kind of matching together, which is really nice. After 2 years of experience now, where are the SNOWPACK tools the most useful for your forecasters compared to earlier years? So where they didn't know. And by the way, I think JT made a wrong comparison. It's not the wheel built on some horse thingy, but I think it's that we are now discovering that there are Ferraris around 20 years now, and we are not using them. And so what do you think was the most useful things for you forecasters in the last 2 years?
I think it's the shift of looking at snow profiles as point observations to this more abstract view that there's regional scale patterns. And it's tough to see those if you just look at maybe 3 different human dug profiles in a region and try to get a mental picture of these big scale things. It's a new type of way of looking at the snowpack, this regional scale. And it's the closest thing, as Florian mentioned, is on the whiteboards when a ski guide draws the main layers they're thinking about. And I think now we have some kind of visualizations that maybe reflect the way forecasters think about snowpacks at these bigger scales. And we're starting to maybe shift the way we think about snowpack patterns because of that.
Right. Concerning patterns, there's a question from Luca De La Role from Livigno Avalanche Forecasting Center. How do you predict the avalanche problems in terms of aspects? So I think he thinks that you mainly consider flat field simulations. So from there, how do you extrapolate to the aspects?
Mm-hmm. That can be difficult, and I guess at this point, these tools are just kind of a starting point piece of data in your assessment. So if I was to work on a forecast in a remote area and I saw there was a weak layer that the models were showing at a certain depth, I would then kind of look through some other pieces of evidence, such as field reports from the past week, the weather station kind of info I have, in looking past cloud cover, and try to just extrapolate based on the bits of information I have. But the model's not really giving us that resolution right now. That's still more into the assessment of subjectively.
Perfect. So kind of starting point and then extrapolating.
Yeah, and my understanding is that there hasn't been a lot of development, at least on the snowpack model side of things, on the virtual slope simulations much in recent years. And I'd be really interested to kind of hear if there's more plans to develop or validate those, because I think before we moved on to doing this in these remote regional scales, it'd be nice to have some more small scale validation and maybe calibration at a site like the study plot in Davos.
In the meanwhile, there was an answer by Stephanie Meyer, who joined forces with Florian. Hello, everyone, she writes. The instability model Florian used is a random forest model, which was trained with observed profiles, including Rutschbrock tests and their simulated snowpack counterparts. The model provides a layer-wise probability of instability given the simulated properties of the layer. That means grain size. Or example grain size and the overlying slab. And she says, sorry, my baby was crying, so I didn't dare to put on the microphone. Thanks a lot for that, Stephanie. But it would be also really nice to hear some new guns in the snow community, what their opinion is about that. And she shared with you the preprint on that topic, so you can dig deeper into that one. Yeah, I think we are getting into our last minutes of this workshop. So if you still have one question, there's Moritz, for example, from SLF. Did you try some matching between the weather model driven simulations and potential simulation runs at the few locations where you have weather stations?
Yeah, we haven't been doing that approach in recent years. At the start of this project, back with Sasha's work with Bruce Jameson, that was kind of the focus. We worked on maintaining about 5 different weather stations that were equipped to run snowpack and did that kind of point-wise comparison. and we haven't done that as much lately.
Yeah. And probably you have again the same problem. What's the truth? Because also weather stations can have some problems with sensors and all the stuff. So if someone is out there having a nice strategy on verifying that, your help is appreciated. Yeah, I think most questions were asked. So I would like to kind of pose to both of you and more an essay question at the end. So it's 5 years you guys are working hard now on that topic. What do you think looks the forecasting day in 5 years? Is there more models that will take over our work and we have to take care about social media comments and posts, or is our daily business looking pretty much the same as it is today? So that would be my question to Simon. And Florian, to you, what can we expect from a simulation in terms of linking still some old Ferraris which are out there but not discovered, for example, the snow micropenitrometer and the things you are doing? Is there potential, and how does that look like in 5 years? Maybe Simon, you start.
Yeah, absolutely. A common theme of discussion whenever kind of talking with the other forecasters at Avalanche Canada is that with more data and models becoming available, that at some point our work will shift from being risk assessment kind of avalanche forecasting into more risk communicators. And as you were kind of saying, improving the way we communicate this information to the public or other users. But that being said, in 5 years, I can see our tools of visualizing and looking at the data a bit better to give us a more complete picture of the snowpack, but in avalanche conditions. But I think it'll still be some more time there to kind of link that all together to directly get an avalanche forecast from it. But we're getting more tools to get more precise and detailed pictures of the snowpack conditions.
But daily routines are more or less the same.
Yeah, with fancier tools.
Great. Looking forward to that one. Florian?
Yeah, I think there are two different themes in your question that I want to speak to. So I think the first theme is really updating model simulations. You mentioned the snow micropenetrometer. And I think here it's worthwhile to mention the scale. I think on a smaller scale, there might be opportunities and it might be possible to update snowpack simulations with observations like these. I think on the scale we're concerned with, we have a scale mismatch here. So I don't really think that sampling lots of snow micropen observations and trying to feeding it into our regional scale simulations will be the way forward. But I personally am a big fan of ensemble modeling. So looking at data assimilation, we can focus on updating and correcting model simulations, but data assimilations are also very closely tied to ensemble modeling, at least some assimilation techniques. And so from that perspective, I think it would be worthwhile to produce snowpack ensemble simulations and then discard simulations that do not match with what we see in the real snowpack. So the updating of the model simulations would be keeping, and now I'm using the word particles because that's the data assimilation method, the particle filter that I'm thinking when I'm giving you this answer here. So individual ensemble members are kept, others are discarded, and that way the model is being updated throughout the season and kept as realistic as possible. And that's actually the way that that I'm having in my mind and that I'm envisioning for our future projects.
Okay, thanks, Florian. Thanks, Simon, for your delightful insights. It was really a pleasure to have you on our workshop, the second season. And I would like to close the workshop now, and I think also close more or less the season. I think unless Norway season is fading out in all parts of Europe, also in major parts of Canada, I wish you all a very nice and smooth transition into spring, the real spring without snow, the one with sun and bicycles. And I hope to see you again for our next workshop, which will probably take place somewhere at the beginning of the season. So when everybody is again pumped and keen for new snow. Thanks for joining us. It was a very, very nice workshop. I have seen that at peak time we had almost 90 participants. This is very, very cool, and hope you can join the next time. Bye-bye from Innsbruck. Ciao.